Hello everyone, my name is Charalampos Gkountas and today I will be presenting our research study titled Structural Credentials of Wire-arc Additive Manufacturing Fabricated Nano-reinforced Aluminum Alloys. This research study was conducted by me, Gavriil, Dimoulas and Evangelos Efthymiou at the Institute of Metal Structures of Aristotle University of Thessaloniki, Greece. First of all, allow me to do a brief introduction about aluminum. Aluminum is a metal chemical element featuring three critical beneficial characteristics. First of all, aluminum is a lightweight element. Aluminum has a low density of 2,700 kilograms per cubic meter, which is equal to around 1/3 of steel's density. Also, aluminum maintains a relatively high strength-to-weight ratio compared to other materials such as concrete or steel. Secondly, aluminum is highly sustainable. Specifically, it is a non-toxic and highly recyclable material as it can be reused repeatedly with minimal degradation across applications. Lastly, aluminum is a durable material. Aluminum offers excellent corrosion resistance and strong performance under various mechanical loadings. In addition to that, it remains stable at elevated temperatures up to 80 or even 100 Celsius degrees. The main process to produce a product from an aluminum alloy is illustrated in figure 1. As you can see, pure aluminum is alloyed with elements such as copper, manganese, silicon, magnesium and zinc, and then we get what we know as aluminum alloys. Then we shape these aluminum alloys into our products. We treat these products with heat treatment most of the times, and then we get our final aluminum product. Aluminum alloys can be shaped into a wide range of product. As you can see in figure 2, we can get aluminum sheets and plates on the top, but as well as extruded rods, extruded tubes and extruded profiles, which can be really beneficial because we have high geometrical flexibility and geometric design. However, which is the motivation for seeking alternative shaping techniques for aluminum? We can find the answer if we see at aluminum's production line. In figure 3, you see that first of all we have to extract the bauxite, which is the primary ingredient of aluminum. Then two processes happen which are named as Bager process and electrolysis. I would like to mention that these three first phases are energy intensive. However, current technology cannot limit the energy demand associated with these three first stages. However, the last stage, which is the product shaping stage through extrusion most of the times, can be significantly decreased by adopting an alternative deposition-based fabrication method, such as additive manufacturing. As you can see at the bottom of the slide, extrusion offers three main advantages, such as the fact that it is swifter than rolling. It offers flexible design of complex section, as I said in the previous slide, and it can generate large scale and thin sections. However, there are some disadvantages. It is highly energy intensive inside the highly energy intensive production line overall. It demands large production runs to justify the costs. It has significant material waste, which is the scrap. As the billet goes inside the die, we have a scrap material, and there is high production and maintenance costs for our dies. So we have to seek alternative shaping techniques in order to reduce this high energy demand and to make the process a little bit more sustainable overall. Additive manufacturing is defined as the process of joining materials to make parts from a 3D model data, usually layer upon layer, as opposed to subtractive manufacturing technologies. As you can see in figure 4, the process is explained schematically. First of all, we have a digital 3D model, which is then sliced into layers, into printing layers. Then the printing process happens and we get the final printed component, the final printed part. The process is illustrated for a typical cementitious material, however, it is the same across different materials. Additive manufacturing, or 3D printing, demonstrates several advantages compared to conventional extrusion. Specifically, it offers large design flexibility, high material efficiency, rapid prototyping, as well as it enables tailor-made geometries. Lastly, it minimizes the material waste as the material is deposited only where needed based on the 3D model data. For aluminum alloys, there are mostly two additive manufacturing techniques used among the 7 existing. Specifically, these are the power bed fusion and the directed energy deposition. In PBF, powder bed fusion, as you know, a metal powder is used to produce high precision and high quality parts. However, PBF is limited to small and medium sized parts. Thus, we cannot use it to produce aluminum alloy sections intended for structural engineering applications. In directed energy deposition, also known as DED, the material is in wire form, it is being melted while deposited, and the method is ideal for a large-scale production. However, disadvantages are also here. As you know, we have hot cracking, porosity, residual stresses, and anisotropy, which hinder the adoption of the process. In figure 7, you can see the hot cracking that occurs while one printing of 6 and 7 series aluminum alloys. Recent literature and experimental studies have shown that the addition of titanium carbide nanoparticles in the mixture of 66:1 aluminum alloys can significantly reduce these disadvantages. We propose to optimize the printing parameters as well. Specifically, we propose the following optimized printing parameters of table 1. The sealing gas should be argon. The heat input should be limited to somewhere around 0.3 to 0.5 kilojoules per millimeter. The welding voltage should not exceed 12 volts, and the material wire feed should be somewhere around 15 centimeters per second. Additionally, the nozzle travel speed should not exceed the 1 centimeter per second, while for interlayer cooling we propose thermoelectric air jet cooling and ultrasonic pinning. Through these proposed printing parameters and with the addition of titanium carbide nanoparticles in the mixture of the aluminum alloys, we consider that the heat affected zones, hot cracking phenomena, the residual stresses, and the anisotropy regarding the mechanical properties are significantly mitigated. As you can see in table 2, these are the mechanical properties of nano-treated 66:1 aluminum alloys. As you can see, we get literally almost no anisotropy on the mechanical properties, and compared to aluminum rod 66:1 tough 6 heat-treated typical aluminum alloy, we have significantly improved mechanical properties. Yield stress and ultimate stress, both of them are increased to 300 megapascals and 350 megapascals compared to 240 and 260 megapascals for typical 66:1 tough 6 aluminum alloy. These are the experimental stress strain curves based on available literature, and we will use these values for the analysis to be conducted at the following stages. The analysis will be conducted in 2 scales. First of all, we will do a cross-sectional scale analysis, conducting a moment versus curvature analysis for the examined section. We will evaluate a total of 6 cross-sections. Specifically, there will be 2 reference extruded profiles made from typical 66:1 tough 6 alloy, and there will be 4 1-fabricated nano-treated 66:1 alloy sections. These alloy sections will feature constant and variable thickness to demonstrate the advantages of 3D printing or additive manufacturing. The cross-sectional behavior will be assessed through moment curvature analysis performed under a typical and representative compressive axial load of 0.2 or 20% of the axial load capacity, which is equal to the yield stress times the cross-sectional area. In figure 4, we can see the examined cross-sections. You can see that the first set of 3 sections will feature an outer dimension of 100 millimeter, and the variable thickness section will also have 100 millimeter external dimensions, but they will have more material added at the corners where we have more stresses. And the last 3 sections will have 120 millimeters external dimensions, and they will again feature thickened corners. In figure 9, we can see the results of the moment versus curvature analysis through the moment versus curvature curves for all the examined sections. As you can see, we get higher moment resistance and curvatures for the sections featuring both WAM production and the nano treatment of the material. As you can see, we reach up to 76.7 bending moment increase, and we reach up to 73.9 increase in the axial load capacity. This happens due to both the material improvement and the optimized geometries when we use the variable thickness sections. The capacity gains are higher than the area gain, higher than the area gains, where the area gain is 7% and 40% for the two sections respectively. Following, we will conduct a structural scale analysis. We will be developing a frame numerical model, a two-story frame numerical model according to the provisions of Eurocode 9. Dead, live, wind, and snow loads will be examined along with seismic loading. The seismic loading will be taken into consideration using the lateral force method. The 6 previously examined cross-sections that I showed you in the last slide will be used as the columns of the prototype frame to evaluate their influence of the global structural response. This is the prototype frame, the two-story frame. As you can see, the total height is 6 meters, while each span's length is 4 meters. We use fixed boundary conditions at the structure's base to simulate a moment-resisting frame, and the column sections will be alternated between the 6 previously examined sections. These are the results of the structural scale analysis in terms of lateral displacements. The seismic combination leads to the most critical lateral displacements. As you can see, for the first sections, the material improvement, the nano treatment led to no reduce in the lateral displacements as initially expected, because we do not have greater stiffness. We only have larger yield stresses. But when we're using the variable thickness sections, we get decreased lateral displacements, and the corresponding drift ratios are decreased. As I said, frames featuring the extruded cross sections and WAM nano treated with constant thickness exhibit equal lateral displacements and corresponding drift ratios. However, consequently, the material improvement did not enhance global stiffness. However, the use of variable thickness WAM sections led to notable decreases in lateral displacements and drift ratios, demonstrating the effectiveness of both optimized geometries and material improvement. As you can see, the drift reduction is 19.6% for the first floor and for the first story, and the drift reduction for the second story is around 12.5%, which is something that we consider to be favorable. However, these drift ratios do not satisfy the limit of Eurocode 9. Thus, in future research, we should examine the utilization of lateral braces or other methods of increasing our lateral stiffness and consequently decreasing our lateral displacements. The structural scale analysis continues with the corresponding capacity factors. Design buckling and bending resistances, NI-BRD and MIRD, respectively will be calculated for each column cross-section according to the provisions discussed in Eurocode 9. Thus, our calculations are Eurocode compliant. Design axial loads and design bending moments will be extracted from the software used for the analysis and will be used to compute the corresponding capacity factors. As you can see, the first sections, the small sections featuring 100 mm external dimensions, do not satisfy the limit of 1, which is the capacity factor. However, when we use the larger sections featuring the 120 mm external dimensions, extruded section still does not satisfy the limit. However, both of the WAM sections, the constant thickness and the variable thickness, satisfy the limit of Eurocode 9. And for the last section, the WAM V120, we conclude that it may be used for additional loading or the construction of an additional story. As you can see, capacity factor decreases due to both the material improvement and optimized geometry. Sections WAM C120 and WAM V120 satisfy the code limit, Eurocode's limit. So, overall, and to conclude, wire-arc additive manufacturing suggests a viable alternative to conventional extrusion for the fabrication of aluminum alloy sections. Optimized printing process parameters and nanoparticle reinforcements mitigate hot cracking, anisotropy, and Hodge phenomena. Nano-treated WAM 6061 alloy achieve higher performance than the reference extruded sections overall, as we saw in both the cross-sectional analysis and the structural analysis. Variable thickness geometries demonstrated the highest benefit at the cross-sectional and structural scale at the cost of using slightly more material, 7% and 40% more material, while our improvements were around 75% and 78%, if I remember correctly. Lastly, at the structural level, only the frame configurations featuring WAM C120 and WAM V120 satisfy Eurocode 9 provisions and allow for extra loading or additional story construction. This was the presentation, and I would like to thank you for your attention.